Welcome to this explainer. Today, we're diving right into the massive, and I mean literally massive, physical challenges of electric vehicles. But more importantly, we're going to look at the incredible virtual tools engineers are using to actually solve these problems long before a single physical part is ever even built. So, if you've ever wondered how the auto industry designs completely new vehicles without wasting millions of dollars on trial and error prototypes, well, you're definitely in the right place. Here's our roadmap for today's explainer. We'll be taking this step by step, starting with the core EV battery challenge, then looking at the power of virtual models, setting performance targets, defining the optimization problem, and finally, finding that mathematical sweet spot. Okay, section 1, the EV battery challenge. Let's just start by looking at the sheer physical reality of replacing fossil fuels with electricity. It really requires a total reimagining of a vehicle's physics. So engineers face this massive trade-off right out of the gate. Check this out. A standard diesel tank weighs, just about 95 kilograms and takes up 85 liters of space. Pretty manageable, right? But to get comparable energy out of a lithium-ion pack, that battery balloons to 700 kilograms and 430 liters. I mean, that is literally 7 times the weight and 5 times the volume. And because of that massive size, this heavy, bulky battery pack completely dominates the whole vehicle's architecture. As you can see, it sits low and wide, essentially becoming the entire floor of the car. And since the battery is the largest cost and by far the biggest contributor to the vehicle's overall weight, getting its size wrong is, well, incredibly costly. Which brings us perfectly to section 2, the power of virtual models. Building endless physical prototypes just to test out different battery sizes is simply way too slow and far too expensive. So to get around this, engineers now rely on systematic model-based design. Basically, instead of welding metal and assembling real battery cells just to see if a concept might work, they run virtual tests. This completely avoids the costly defects of physical prototyping. It keeps iteration cycles incredibly short, and ultimately, it saves an immense amount of time and money. By using software tools like the Virtual Vehicle Composer, engineers can seamlessly connect to the vehicle's physical traits with its software. And hey, don't worry, you absolutely don't need to read the specific code or try to map every single line here to appreciate how interconnected these blocks are. The main takeaway is that the environment, the driver commands, the controllers, and the physical vehicle are all talking to each other in this one unified simulated space. Let's break down how this simulation actually builds logically. The software essentially runs just like a real test drive. First off, the virtual driver sets a target speed. Second, the system sets the necessary brake or acceleration commands. Third, those commands are translated all the way down to lower-level actions, like motor torque. And finally, the simulation calculates the exact physical response. And the crazy part? This is all happening in milliseconds. Okay, moving on to section 3, setting performance targets. Because before we can optimize anything in that simulation, we have to know exactly what parameters and requirements this electric vehicle actually needs to hit. Engineers establish a really rigorous baseline by setting system-level targets across the board. For instance, they evaluate fuel economy and total range by running standardized drive cycle tests. To test acceleration, they run virtual wide-open throttle tests, which is exactly what it sounds like. And for the cost, they just lock in a specific dollar amount per kilowatt hour. To show you just how critical this target setting is in the real world, consider the MIT Solar Car team. So during their endurance drives, their battery pack is charged only by solar panels. They actually used logged test data to carefully analyze the trade-off between battery weight and capacity. By modeling their requirements perfectly, they managed to design a smaller, lighter battery that genuinely improved their performance during really demanding hill climbs and, cloudy weather when they didn't have as much sun. All right, section 4, the optimization problem. This is where we hit the real climax of our engineering challenge, translating all those targets into an actual mathematical optimization problem. This brilliantly illustrates what it looks like when engineers start playing with what they call design variables. By literally simulating the addition or removal of battery cells, both in parallel and in series, they can completely alter the physical footprint of the pack. And changing these variables changes absolutely everything: the overall weight, the cost, the range, and of course, the power. For the sake of this explainer, let's look at a really specific puzzle. We start with a baseline vehicle that gets 371 kilometers of range, costing right around $7,500 for the battery. But our goal here is to mathematically stretch that range past 400 kilometers, while simultaneously and aggressively pushing the cost down. Basically, we want a much better car for less money. Which leads us to Section 5, finding the sweet spot. Finding that perfect balance is notoriously difficult. So let's dive into how the simulation software actually hunts down that optimal configuration. To pull this off, engineers literally feed an objective equation right into the software. This function basically demands that the system finds a perfect balance between the lowest possible price and the highest possible range. But there's a catch. It's bound by some really strict constraints. It absolutely must maintain a range of over 400 kilometers, and it has to still hit 0 to 100 kilometers per hour in under 7 seconds. Now, the issue is that simulating every single possible battery configuration to find the winner is just way too computationally expensive and slow. So the software smartly relies on what are called surrogate models. You can kind of think of a surrogate model like a simplified treasure map. The software uses it to predict where the best design point might be. It samples data around that specific area, and then it pinpoints the absolute optimal pack size, all without wasting time calculating every single dead-end combination. Seeing how seamlessly we can go from this massive physical weight problem to a perfectly optimized digital solution just leaves us with a really fascinating thought. I mean, if these virtual tools and surrogate models can so flawlessly solve the highly complex EV battery dilemma, what other massive physical systems out there, from our global power grids to deep space aerospace networks, are just waiting to be entirely re-engineered in the virtual space? It's a lot to think about. Thanks so much for following along with this explainer, and keep questioning how the virtual world is shaping our physical reality.